All right, so now we're going to talk about Vesper theory. Okay, Vesper is this very fancy name, valence shell electron pair repulsion. Uh, Fancy way of saying really what we're going to be doing is going from our Lewis structures that we just learned how to draw. The Lewis structures are 2D representations. They tell you who's bonded to who and where the electrons lie within a molecule. But they don't actually tell you the 3D shape of a molecule, right? Molecules are not two-dimensional. They have 3D geometries. So the Vesper theory is how we're going to go from our 2D pictures, our 2D Lewis structures, to the actual, holy, Hulu's apparently updating itself, I apologize, to the actual three-dimensional shape of the molecule. For ammonia, this is what we call a trigonal pyramidal shape. And we'll learn about all those different types. But that's the name of the game for these chapters, is going from your Lewis structure to the actual three-dimensional structure of the molecule. Okay, this idea of, again, Vesper is valence shell electron pair repulsion. And the electron and the repulsion part are really the keys here, because this is the key to Vesper theory. This idea that we're going to talk about electron groups and the fact that they want to be as far away from one another as possible. Okay, so this is often represented using balloons, because if you tie the end of two balloons together, they'll sort of stick out as far away from each other as possible. So if you have 1, 2 electron groups, they're going to be pointed on opposite sides, right? They want to be away from each other. They're, of course, attached by your central carbon in the middle here. So, I mean, they can't just separate and fly apart, right? These are bonds within a molecule. But they're going to be as far away from as possible. So if there's only 2 of them, the way that that happens is they just sit on either side of that atom. If there's 3 of them, 1, 2, 3, they'll actually, so this is, real quick, this is what we call a linear shape right here when they're far away from each other in a line, okay? When we have 3 of them, they're again going to orient themselves so that they're as far away as possible. And the way that they do this is what's called a trigonal planar shape, right? So they all sit in the same plane, they sit flat, but in a triangle shape. They're kind of making up these 4 corners, or I'm sorry, not 4 corners, 3 corners of a triangle. And then the last one is when we have 4 and we're trying to, they sort of separate out into this weird structure that's called a tetrahedral. Okay, so that's, I don't know if you guys know that old-timey game Jacks, but that's that shape that they have where it has 1 pointed up and then the other 3 are kind of arranged as a bit of a triangle underneath. Okay, and that's again when we have 1, 2, 3, 4 electron groups, they'll arrange themselves in a tetrahedral geometry. Okay, so the number of electron groups will correspond to the electron geometry. So what do I mean by electron groups or electron regions? Okay, so these are either lone pairs or a covalent bond regardless of order, meaning regardless of whether it's a double, single, or triple bond, it will still only count as 1 electron region. So we're always only looking at the central atom, right? We're not looking at the constituent atoms. They won't dictate the shape of the molecule. So when we're talking about counting electron regions, we're looking specifically at this nitrogen here in the middle, the central atom. And in this case, it has 1, 2, 3, 4 electron regions, right? So 3 of them are bonds, single bonds, and then the 4th one is the lone pair. So this would have 4 electron regions. Okay. Let's calculate the number of electron regions in boron trifluoride. So everybody take a second, see if you can't do that. Again, which atom am I paying attention to? only this central atom here. I'm not looking at the fluorines. The fluorines are going to tell me the shape of the molecule. Only the central atom dictates the geometry of the molecule. So this has 1, 2, 3. So this would be 3 electron regions. Remember, boron is one of those exceptions where it only needs 6 electrons in its valence shell. So it's actually perfectly happy despite only having 6. So this particular molecule would have 3 electron regions. Okay. The number of electron regions, as we saw before, they correspond to hybridization, which actually we don't really have to know for 3A. So don't worry about that. We're going to worry about this correspondence, the number of electron regions to the electron geometry, right? So if we have 2 valence electron or 2 electron regions, that would be a linear shape. 3 electron regions, that's a trigonal planar shape. And 4 electron regions is a tetrahedral. Okay. Now, eventually, we're going to distinguish between the electron geometry and the molecular geometry. Okay. So the electron geometry is how the electrons are oriented. The molecular geometry is specifically the arrangement of just the atoms, right? So it's sort of like ignoring the lone pair. We're going to break this into 2 parts. This first part, we're only going to be concerned with atoms where the electron geometry and the molecular geometry are the same. So they're going to be the same as long as that central atom doesn't have any lone pairs. Okay, so let's see how we would do this from scratch. CO2, if we went through and we drew the Lewis structure, it would look something like this. And you guys can convince yourself of that by going through those steps that we did in the previous chapter. And then we're going to count that there is 1, 2 electron regions. And that's what leads me, so 2 electron regions. And so that's what leads me to my linear, both electron geometry and molecular geometry, right? Because the central atom, that carbon, doesn't have any lone pairs. So the electron geometry and the molecular geometry are both going to be linear. We saw that example of boron trifluoride, which had 3 electron regions. And since that central atom doesn't have any lone pairs, both the electron geometry and the molecular geometry is what's called trigonal planar. All right, and then lastly, if you remember, we did CH4 on one of the first lectures. That would be something like this is what the Lewis structure looks like. That has 1, 2, 3, 4 electron regions. And since that central atom doesn't have any lone pairs, the electron geometry and the molecular geometry is that tetrahedral shape.